Yeah, I feel like I should apologise before this paper. It's an extract, a hacked extract from my current book project. I'm experimenting with a few ideas, and I'll read it as well, which might help it be a little bit more cogent. So bear with me. This talk proposes a thought experiment based on biologist Stephen Jay Gould's evolutionary tape from 1989. Gould's experiment aimed to explore whether the evolution of life was a deterministic or contingent process. Imagine we rewind evolution back into the mists of time and set it off again, like a wind-up toy. What would happen? Gould believed that evolution was historically contingent on so many factors that it's impossible to tell. Nothing might happen, or species radically different to contemporary humans, mammals, insects, and viruses might evolve. It's impossible to say. He felt that it's highly unlikely we'd get the same result, however. The experiment is, of course, impossible to run and contentious, but it prompted decades of fruitful debate. So let's imagine that the global digital infrastructure that enables much of contemporary culture and society disappears overnight, and it's rebuilt by a new generation of mathematicians and engineers. Well, what would the new infrastructure look like? How would it perform, and what would it be capable of? Would it be identical to the infrastructure we have now, or unrecognisable? Would it be embedded with the same biases and inadequacies of contemporary infrastructure? Would it be oriented towards business or pleasure or spirituality? Would we have desktop computers and mobile phones with CPU, RAM and storage, or alien, perhaps even organic devices? The problem is, of course, intractable, touching on fundamental problems in mathematics, logic and engineering, as well as canonical problems in history and philosophy, such as determinism and the social construction of technology. The experiment focuses our thinking by forcing us to consider the boundary conditions that limit the logically possible scenarios, but it also encourages us to view digital infrastructure as at once natural and contingent. And finding critical perspectives that can help us understand this degree of complexity is tricky. And I have my suspicions that the theory of emergence used in the philosophy of science can help. So Ye-Won Kim notes that there has been a significant increase in philosophical writing about emergent theory since the 1990s, primarily in philosophy of science. The theory has ancient roots, been explored by ancient Indian as well as Greek philosophers, including Aristotle. And contemporary emergence theory is strongly influenced by the British tradition first articulated by John Stuart Mill in his System of Logic from 1843. But the theory disappeared from intellectual discourse from the 1930s to the 1970s, briefly resurfacing in the writing of Michael Polanyi in the 1960s, before being applied to a wide range of fields from the hard sciences to sociology in the latter decades of the 20th century, and is currently seeing another resurgence as work in quantum theory and philosophy exposes gaps in purely physics. As Philip Clayton suggests, emergence theory refers to, quote, and autonomous from that base, end quote. The classic example of it is water, which has characteristics such as transparency and liquidity and an ability to quench thirst that emerge from its constituent parts of hydrogen and oxygen in unpredictable ways. And unpredictability is important in terms of the theory of emergence. Philosopher of cognition John Searle extends this analogy to consciousness, claiming that consciousness is supervenient upon the component parts of the human brain, from molecules to tissues to neurons. And That is not to make a simplistic claim that the relationship between the human brain and consciousness is fully understood, much less that human consciousness could be reproduced mechanically with our current state of knowledge. But in the absence of appropriately powerful scientific theories demonstrating the detailed way in which consciousness emerges from grey matter, it is quite reasonable to assume that it does, however, in some way emerge from our brains. In much the same way, I would like to suggest, or merely point out, that global digital culture and society is supervenient upon its conceptual and material infrastructure. More specifically, I claim that the digital world is an example of weak emergence, where, quote, a system's macro properties can be explained by its micro properties, but only in an especially complicated way, end quote. So weakly emergent phenomena demonstrate what Marc Bedeau describes as explanatory incompressibility, meaning macro phenomena are, quote, causally reducible to the micro in principle, but the reductive micro explanation is especially complex, which I think is quite a good explanation or description of global humanities, global cyber infrastructure. So Martin Heidegger might have suggested that emergence theory describes the process of unconcealing or bestand, but it's useful for our purposes to have it tightly coupled to scientific inquiry. In my book, I'm trying to connect it to more humanistic theories. Digital modernity's micro-components are fairly obvious. Microchips and their associated circuit operations, and at a higher level of abstraction, the von Neumann hardware architecture connected by digital networks. The remarkable complexity and range of unpredictable phenomena basic computing systems such as these can generate is well established. The canonical example offered is usually Cambridge mathematician John Conway's Game of Life, comprising simple cellular automata that propagate within a grid pattern according to simple rules. And the little game generates a range of unpredictable behavior with, quote, the majority of sufficiently large patterns exploding quadratically to fill most of the 2D plane, end quote. So the supervenient relationship of Game of Life to its computational infrastructure is self-evident, but even at this modest scale, incompressible. Expanding our analysis outward to global digital infrastructure may well be crazy, as we need to do it in our analysis of the digital world. And what we get conceptually, if we move from the game of life out to global digital infrastructure, is a Cambrian explosion of not only computational but socio-technical complexity that confounds explanation. And that's why an interpretation of digital infrastructure is a political act, of course. It can be reduced to its component material parts easily enough, microchips and von Neumann architecture, but its meaning cannot be reduced to those same components. Rather, and I'm aware this is quite a bold statement to make, I need to work out exactly how to frame it, meaning emerges from those components within the boundaries imposed by the natural world. It's fascinating to consider, for example, the boundary suggested by Pascal's triangle, produced in 1654 but known to Indian and Chinese mathematicians centuries earlier. The triangle forms an array of numbers of binomial coefficients that emerge in probability theory, combinatorics, and algebra. It can be used for binomial expansion of algebraic expressions using the natural relationship of binomial coefficients in geometric form to ease calculation. The form of the triangle emerges from and is expressed in nature in the same manner as a Fibonacci sequence. Perhaps more apposite to discussion of digital infrastructure is the Fibonacci spiral, found in physical form throughout nature in the form of seashells, flowers, and weather systems. So my argument that I'm sort of grasping after, and I'm not sure how strongly to present this, But my argument is that the infrastructure that enables digital modernity is naturally complex in much the same way, both constrained and enabled by the logic of mathematics. People uncomfortable with this level of conceptual reduction might like to consider the centrality of mathematicians such as Gottlob Frege, Bertrand Russell, Alonzo Church, Alan Turing, and Kurt Gödel to the development of computer science. The ability to mechanize the world using the abstract power of mathematics combined with manipulation of symbols lies at the very core of digital culture and society. And yet our thought experiment, is a reminder that our computational infrastructure is far from ideal in the Platonic or any other sense. The beautiful mathematical resonances described by Douglas Hofstadter and Gödel, Escher, Bach are a far cry from the often ramshackle and always politically and economically mediated infrastructure enabling the digital world. And yet this is not to deny the wonder of contemporary digital infrastructure, of course. There's a marvel of human ingenuity and engineering. As Beatrice Farsi notes, we can either view the boundary identified by early 20th century mathematicians as evidence of the failure of formal systems, or surmise that, quote, the incomplete and incomputable are not errors or stopping points for axiomatics. Rather, they show that indeterminacy pertains not only to the empirical realm, but the formal too, end quote. So the fact that our global computational infrastructure is inherently limited is not only a function of human failings in design and engineering and socio-cultural politics and economics, but an expression of the natural world, like a gnarled tree or a malformed seashell. So I'm not sure how much sense all of that made, but that's where I'm going to stop. I hope it provides some food for thought. If critical infrastructure studies can offer anything, I think it should help us defamiliarize contemporary infrastructure to help us look on it with fresh eyes, and in doing so, not only see it more clearly, but imagine alternatives. Thank you.